Hi, I'm Carlton Coffrin.
And I am Line Roald, and in this video on convex relaxations in power system optimization, we are going to talk about convex relaxations and their role in AC optimal power flow problem. So let's first start to revisit the AC optimal power flow in order to sort of look at where does non-convexity occur in this problem. So for those of you who have seen the previous videos, this will be a little bit of a recap, but we want to make this very clear. So when we look at this problem, one place where a non-convexity occurs is in this voltage magnitude constraint over here. So you see that when you write this out in real variables, you have these squared terms in the real and imaginary part of the voltages. And when we draw this constraint in the 2D plane, we see that we get this donut shape, which has kind of the outer circle here is the upper voltage bound, and the inner circle is the lower voltage bound. And it is clear that this lower voltage bound introduces a non-convexity in this constraint because it causes this hole in the feasible space. So the feasible space here is really the blue part of that picture. So the question is also, are there any other non-convexities here?
And I think it's worth mentioning at this point that to have a convex relaxation of a problem, all of the constraints should be convex. So you really need to identify every source of non-convexity in the problem.
Yes. Okay, so if we now take a closer look then at the whole problem, what we really see is that actually all of the non-convexities in the AC optimal power flow can be kind of linked back to these products between voltage variables. So what we can do is that we can introduce a new variable, wij, into this problem, which is now equal to, so wij is equal to the product between the voltage I and the complex conjugate of the voltage j. And if we introduce this into the problem, we will see that it looks like this. So now we have replaced all the voltage products by the W variables, and we have put in this equality constraint wij equals to Vi times complex conjugate of Vj. And now if we look at all the constraints, we see that this constraint is now linear, this constraint is linear, the nodal power balance is linear, and the power flow constraint is also linear, because we have the voltage products there. Our power flow constraint for the power magnitude on the transmission line is convex, and we also have a linear constraint on the angle differences. So really now all the non-convexity in this problem is inside this equality constraint that describes the mapping from this variable W to the voltage variables. So the question that now arises is, how do we really convexify this constraint? And in this video, we are going to talk about kind of the original convex relaxation, which is recognized as one of the first papers on convex relaxations in optimal power flow problems. It is also one of the easier relaxations to derive, so that is why we want to introduce it here. And then we will come back to other relaxations that are there later. And we are also not going to go very much into detail, because this is really about you getting an understanding and an intuition for what a relaxation is. Okay, so let's go back to this constraint. So as we have seen, if we are able to convexify this constraint, we are going to have a convex problem. And the key thing we need to try and do here is that we cannot keep that constraint as it is, because it is non-convex. So what we want to do is to find a convex representation of this constraint, which is by design going to lack some of the information, but it is going to keep as much information about the mapping between the voltage variables V and this lifted variable W. So it's maybe also worthwhile to note here that these W variables are called lifted variables because we are introducing new variables into the problem.
Yeah, and also because there's many more of them than there are V's. So we have one V for every node in the network. Now we're going to have one W for at least every edge in the network and maybe even for every combination of buses. So we're lifting to a higher dimensional space by introducing the W's. I think it's also worthwhile to note that designing convex relaxations is a bit of an art. There isn't like a clear-cut guide for how do you do this. You just need to stare at this equation or this system of equations and then have a brilliant idea and then derive it why it actually is a good representation of the original non-convex constraint.
Yeah, and I think we are going to get back a little bit to that when we are talking about that there are many different relaxations that you can use, and different relaxations might be good for different kinds of problems, depending on what type of problem we are trying to solve. Okay, so let's get into how we are going to convexify this constraint. So if we start out from this constraint, this is obviously true.
Yeah, simple tautology.
Yeah. And then from this constraint, what we are going to do is that we are going to take the absolute square on each side. And this is already where we are starting to lose some of the information, I guess, about from the original constraint.
Yeah, so we'll talk a little bit later with a numerical example, but anytime you take an absolute square, you lose the phase information of a complex number.
Yeah. Okay, but so this is a very key observation that we can take this absolute square and then we can regroup those variables over here such that we obtain this equation. So we have now the absolute square of the product between the voltage variables on one side, and then we have the absolute square of each of the voltage variables separately on the other side. And now if we go back to our W variables, we can write this equation down as our W variable. So we have now the absolute square of the W variable ij on one end, and then we have the W variable for each of the nodes, like the Vi times Vi, which Wii and Wjj on the other side.
And I think it's worthwhile noting that this is a valid constraint for any power problem because we derived it from just the product of the voltages. You could take this constraint and add it to any problem where you're producting voltages and it's not going to remove any solution.
Yeah, so what we were saying here when we were saying that we were starting to lose information as we were taking the absolute square is that we have a equality that contains less information than it did originally at the top, but it is still a valid equality for any power problem. So for any problem where the first equality, which is kind of trivial, holds, the lower equality here will also hold.
Yep.
Yeah. Okay, so then we should look at this constraint and see, is this now somehow magically, did it become a convex constraint? So we can draw it. And if we draw this, so this picture over here shows the feasible space of the equality constraint, where we have projected out the Wjj variable.
It also includes the voltage bounds because we know these bounds are kind of like 0.09 to 1.1. That's why we have kind of a cutoff cylinder in this picture.
Mm-hmm. And what is important here to note is that this is a cylinder that has these kind of walls that looks like this donut shape that we have also seen before. But it is clearly a non-convex constraint because the inner part of the cylinder is not included in the feasible space. So there is a hole here in the middle. So what can we do to make this convex? Well, we can relax it. And we can take away, instead of enforcing this with an equality, we can say that, okay, we have an inequality here. And now if we draw the same picture for this constraint, we can see that we are actually sort of just filling in the middle of this cylinder such that we now have this filled in cylinder,
yep.
essentially. And this is now a convex constraint.
So the one last thing that's really important to think about when you're doing relaxations is you have to prove that this final relaxed constraint is both convex and is valid subject to the original constraints. So this sequence of operations where we started from a clearly true tautology in the original problem, and then we apply arithmetic manipulations that only make it a weaker and weaker constraint, is the arithmetic proof that you're not removing any feasible point from the original set.
So if you would add a constraint that would become more restrictive, then you would no longer know that you have a relaxation. Right?
Yes, unless you proved it. And so that's one of the games when you're developing relaxations is you may come up with a new constraint, but you have to go through and arithmetically prove that that new constraint does not remove any point in the original problem.
Okay, so now if we go back to our full problem, so what we had originally was that we had this optimal power flow, AC optimal power flow problem, where we had this equality constraint for the W variables as our first constraint. You see now here we have replaced that with the inequality we derived on the last slide. And that is really now a relaxation. So because we have replaced this constraint by this weaker constraint, we have increased the feasible space of our optimization problem, which means we have a relaxation. So now, if we look at again the convexity of each of our constraints, we can see that all of the constraints here are now really convex. And also we assume that we have a convex objective. So this is what is called the SOC optimal power flow problem, because this can be represented as a second order cone optimization problem, which is a good type of problem to try to solve. There are efficient algorithms available for that problem. Okay.
Great.
Anything else to add about this now?
No, I think this is great. We have a convex relaxation. All the constraints are convex. That's what you want.
Yeah, so this is one convex relaxation.
Right. So there are many other convex relaxations of the AC power flow, and I'll just give you a brief overview of kind of the broad strokes of this. So if we have our non-convex AC set represented by this weird squiggly space, one of the weakest relaxations that has ever been developed is called the copper plate relaxation, and this is just a linear program, so it's very fast and scalable to compute, but it's very weak. It's big area outside of the AC.
Yeah, so this is essentially where you are not taking into account any constraints on the power flow.
On the network, yeah.
You have no network constraints.
You know the bounds on the generators and the demand, and that's basically it.
Yeah.
The next one would be the network flow relaxation, where you can kind of push power anywhere in the network, but there's no losses, and it's a very weak relaxation. But again, this is just a linear program, so it's very fast and quick to solve. Then we have our SOC relaxation, which is the one we just derived for you. This one is a nonlinear but convex relaxation which captures line losses and is where you're starting to get a pretty accurate representation of the whole system. Then there are other relaxations like the QC relaxation, which is also in the same class as the second order cone, but it's proven to be slightly tighter than the second order cone. One relaxation which has gotten a lot of attention in literature is the SDP relaxation, which is based on semi-definite programming. And it's actually has been shown that it's not stronger or weaker than the QC relaxation, so they both live inside of this SOC relaxation. And then you have very sophisticated methods like the moment hierarchies or the sum of squared methods, which actually result in SDP optimization problems, but they're growing in complexity, and you can basically turn up the accuracy of these methods until they exactly fit the AC feasibility space, but you're paying a price of a bigger and bigger model.
Yeah, so you can actually represent the feasibility space exactly, but still have a convex optimization problem.
Correct, but you're not. It's a very subtle point, because as you get a more accurate representation of your non-convex problem, your convex, moment hierarchy problem is getting exponentially large in its size. So you're not, even though it sounds like, oh great, convexity, that's going to be really fast, you really have to test it in practice because the model is getting very big, and that slows down the SDP solver.
Yeah. Okay, so maybe also to make one comment about this figure, as you are putting these relaxations sort of inside of each other, what you are showing is really that you get something that is a better and better representation of this original little jellyfish. So it's not arbitrary how these kind of are put on the inside of each other.
Yes, and not only that, every one of these nesting properties needs to be proven arithmetically. And so I'm actually leveraging a number of papers which have proven the relationship between all of these relaxations.
Yeah, and also again, just to recap, because we talked about this in previous videos, but not exactly here, really what you want from a convex relaxation is that it is sort of as tight as possible around this little AC jellyfish as possible.
So going into the derivation of all these relaxations and how they work is clearly outside of the scope of this kind of introductory videos, but I would highly recommend this forthcoming survey paper, which goes into the mathematics of all of these in detail and is really an excellent reference for all the different methods that we've touched on here.
Mm-hmm.
Now, moving on to more intuitions of what's going on in relaxations like this, we're going to go over two kind of core challenges that you face when using or developing relaxations. And the two challenges have to do with line losses and Ohm's law. So let's first look at the challenge of line losses. So as we talked about in a previous lecture, the AC line losses are kind of inherently non-convex, and that's because they have a quadratic structure and it's a strict equality constraint. So the equation here is showing explicitly what I mean there, but the picture on the right is in the intuitive idea. So as you push more and more current across the line, you're going to have a loss which is quadratic, and you have to be on the surface of this cone. So it's kind of a fundamental thing. If you're going to convexify the power flow, you have to convexify this current as well, this quadratic current loss, which basically means you're going to go inside of that current cone right there. And what this means for you practically, you can see the sign of the inequality here, is that on any line in the network, you can kind of throw away power. You can make the losses bigger than they should be in a real network.
Mm-hmm.
Now, we've been talking about current flow, and we haven't really been talking about this voltage stuff. So I just want to show you how the relaxation of the voltage products that we derived for you in this lecture actually leads to this kind of line losses being too big property. So here's our definition of what line losses are. If you expand it out, you get this product of the V variables. And then if we look at that product in the W space, we get this type of expression. Now, recall that normally Wij squared should exactly equal Wii and Wjj, but in this case, to make the problem convex, we've said, okay, Wij can be smaller than it should be. Now, if you look at the expression where you have the Wi's minus the Wij's and the Wjj's, if Wij is getting smaller than it should, that quantity on the right-hand side of the equation is going to get larger than it should, and you're going to have excessive line losses.
Mm-hmm. Yeah, this is also maybe a good example of how we are lifting the variables. Maybe also to mention, in the original equation, we had two variables, Vi and Vj, and here we actually have 4 variables, or 3 variables, really.
3 complex, 4 real numbered values.
Mm-hmm.
Yeah, so there's more degrees of freedom.
Mm-hmm.
And the other intuition we'd like to give you has to do with the relaxation of Ohm's law and kind of a fundamental challenge with using these absolute square types of relaxations. So the key thing to observe here, and we mentioned it previously, is that this absolute square cannot capture phase angles. So the phase shift in the system. So let's look at that arithmetically. Let's define Wij to have a real and imaginary component. You know, that's the rectangular form of the complex number Wij. We can also think about it in its phase space. So Wij has some magnitude, and it also has some angle, theta w. And then, of course, we can connect these two using the cosine and sine as follows. This is just the application of standard complex numbers to this particular w variable. So let's think about this particular constraint. So wij squared equals, that equals the real part squared plus the imaginary part squared. Okay, so we're just expanding out the left-hand side of our valid inequality into real numbers. Now replace WR and WI with their kind of polar representations. And what you can see here is that you can collect out a wij squared, and then you get the sum of cosine squared plus sine squared, which is just 1. So what I'm trying to show here arithmetically is that when you take the absolute square of wij, or any complex number for that reason, you're basically multiplying out all of the phase information into 1, and you're really only going to capture the magnitude of that variable. So what does this mean for power flow relaxations? Let's think of an intuitive example of the second order cone relaxation, which we've talked about in this lecture. And the key thing here is that we know because of Ohm's law, in a network like this, the power should split kind of relative to the resistance on these lines. So you should see less going down the left path and more going down the right path because there's less resistance on the right path. But what this relaxation allows you to do is send an equal amount of power on both paths, or actually send more down the more resistive path, because it doesn't capture the information about the phase that is around this cycle. And this was observed or described as called virtual phase shifters in this paper, which is a very interesting paper I would recommend checking out. And basically what they were showing in this paper is if you had a sufficient number of phase shifters in your network, you could kind of set them to correct for this Ohm's law relaxation, and then the second order cone relaxation would be a very accurate representation of how you could operate your network. But it's important to note it does require very many phase shifting transformers, so that would be like one for every non-tree edge in your network, and that's many, many more than you would find in a typical power network.
Yeah, and it would also mean operating them such to make sure that the relaxation is exact,
right,
rather than
it's kind of
actually help the system operate correctly.
It's kind of a reverse logic. If you wanted to operate the system at its kind of most efficient point, then you could set them all up like this. But typically it's kind of the other way around. You know, the operators want to set them a certain way, and then the economics has to follow what the operators want.
Yeah, you typically want to set the phase shifter such that the system operates, kind of co-optimize the phase shifter itself, yeah. Whereas here you would be required to set it to a certain number.
Correct. Yeah. Now, it's important to note that in this W, there's nothing fundamental about this W space that doesn't let you represent a phase. So an interesting thing you can do is if you want to recover the phase of the Wi and Wr variables, you can take their ratio and then take an inverse of the tangent function, and you'll actually recover what is the phase of the W variables. Now, that's kind of interesting to know. Of course, this is a crazy non-convex constraint, but if you want to start, say, incorporating the effects of Ohm's law, you could look at convexifying this constraint, and people have done that. Mm-hmm. Okay, so next I actually want to talk briefly about feasibility of convex relaxations. So this is situations where a convex relaxation actually gives you an AC feasible solution. So let's just begin with a little thought experiment in the abstract. Normally, when the typical situation when you're using relaxations is that you have your non-convex set, then you have your bigger convex set, and there's some optimal feasible point inside of your non-convex set, and there's an optimal point in your convex set, and then we have some relaxation gap between the true feasible solution and then the relaxed optimal solution. It would be amazingly cool and convenient if somehow the optimal solution of the AC feasible problem just touched the frontier of our convex relaxation. So in this case, basically the relaxation's optimal solution is also the optimal and feasible solution to the original non-convex problem, and there's no relaxation gap at all. So this is super exciting if it happens, because one, it provides you a feasible solution to your original non-convex problem, and you've done that using a fast, convex algorithm, but it also gives you a proof of global optimality of that feasible solution to the non-convex problem, because we get global optimality with the relaxation, and it's a bigger set than the original. If it's also feasible, it's a global optimal solution to the original problem as well. So this was observed in the AC optimal power flow problem on a number of cases that are in the MatPower benchmark set in this very seminal zero duality gap optimal power flow paper. So this was a very interesting and exciting observation that's generated a lot of attention for convex relaxations in the power systems community. Now, this begs a very important question. Will this SDP relaxation always provide a feasible solution to the AC-OPF? And that is kind of, when you observe it on a lot of data, that is a very natural thing to ask. Can you prove it will always be the case? Now, I'll just give you a simple argument why you should be worried or worrisome about such a claim. We know from previous works that this general form of the AC-OPF problem is NP-hard, and we also know that this SDP algorithm is a polynomial time or a fast algorithm. So if the SDP relaxation of AC-OPF was always feasible, then we would be showing something along the lines of P is equal to NP, so this very hard problem is easy to solve in practice. Well, easy to solve in general, I should say. And this is kind of like a too good to be true result. It would be wonderful if it was true, but it's a good reason to be skeptical.
And maybe we should also just say here that if you are watching this and you're like, what is P and what is NP, we would like to refer you to one of the previous videos where we are explaining this in more detail.
Yep. And in fact, some very interesting papers came out around the same time as this original observation, which really examined the limitations of using SDP for a proxy for non-convex AC-OPF, and they made very interesting observations about some cases when it wasn't providing a feasible solution and kind of different ways you could push it towards a feasible solution. So the next thing I want to talk about is why was the SDP relaxation feasible on a lot of the cases that are available in MatPower? And this has actually been one of the topics that I've put a lot of my effort into understanding, because I was so curious how it could be that effective in these kind of realistic test cases. The first reason that I found was because the objective function in a typical AC-OPF study is extremely friendly. So it's basically some kind of either generator fuel cost minimization or some kind of a line loss minimization problem. And why is that a particularly friendly problem? Because we've talked about before, one of the fundamental challenges of relaxations is that they can throw away power on the lines, or they can increase the losses higher than they should be. The objective function, if it's trying to minimize fuel or minimize losses, has a natural it's a natural function to force it to be a strict equality. So kind of it's encouraging if there exists a solution where the losses are tight and exactly equal to what they should be, you will find it. So that was the first kind of major thing that was encouraging this to be tight. The next thing that I observed was that there were no binding constraints, or little to no binding OPF constraints in these MatPower test cases. So the lower voltage limits weren't getting hit in most of the cases, the line flow limits were not getting hit in most of the cases, or just were omitted from the data entirely. And this is actually is a big advantage for a convex relaxation, because when the constraints of your problem start to become important is when the relaxation will want to cheat and want to increase the line losses to do something tricky. And if they don't exist and you're really solving problems without all those OPF constraints, it's not clear that it's actually a hard problem anymore. Remember, those proofs of hardness were done on all the constraints, with all the constraints in the original problem. So there's a very detailed technical report where I discussed a lot of these details, a lot of these points in greater detail with some very clear examples. Now, I would like to point out that since making all these observations, we have tried to improve data sets and put in a lot of the information that was missing, increase the constraints that are active. And in those cases, we're seeing that in about 50% of the AC-OPF cases, the SDP relaxation is finding a feasible solution. So that is still very exciting. That means maybe half of the cases we know of are somehow easy to solve, and that's good news for everyone. But for the other remaining 50%, there's interesting work to be done in developing tighter relaxations or developing new methods.
Yeah, so I guess the takeaway here is really that you might be lucky sort of and have a case where it works, and that is great. But you should also be cautious that it could be that your case is actually quite hard and this doesn't work directly. So.
Right. And I think that just as a general rule, if you're not providing an analytical proof that your method is fast and will always work, you need to do very extensive studies and look into how good is the data you're using and how and test on many test cases to really strengthen your claim that the method will work in practice. Will the SDP relaxation, when will it be AC feasible? There are some very nice results that develop this idea of exactness. I would usually call that tightness. And the idea here was that to basically, can we modify the AC-OPF problem just slightly with maybe some not major tweaks to allow an SDP relaxation to be tight in all the cases. And one of the key ideas in these results is to actually allow buses in the network to consume power. So like you have, say, a virtual load at every bus in the network, and it can just draw power out because it's not efficient to have the power in there. So why does this help the SDP relaxation become feasible? Well, if you have this kind of situation where you're throwing away power on a power line and that's somehow advantageous to the optimal solution, you can always kind of convert it into a tight constraint by moving the power you're throwing away on the line onto one of its neighboring buses. So that's the basic idea behind this throwaway power assumption. So another interesting idea that's come up is, so let's say you have your solution to the SDP relaxation, but it's not AC feasible. What can you do then? So if you don't want to change your problem, but you just want to find an AC feasible solution. One idea that has been proposed there is to change the objective function slightly to guide the SDP into an AC feasible solution. So basically what you're going to do, if the original objective function was at some function of the generator outputs, we're going to add a new term and multiply it by some penalty parameter p, and we'll have some function of the decision variables v and sg, and then we'll kind of use this penalty term in these functions to drive the SDP away from maybe its favorite solution and towards an AC feasible solution. So there's a number of papers which have delved into this idea in depth, and they've had some very nice results for finding feasible solutions. So I would recommend checking those out as well.
Yeah, maybe also at this point we should say that, I mean, as Carlton was describing before, the objective function of these problems are typically very friendly because it is a good thing to minimize losses. As we have discussed also in previous videos, is that there are many problems that contain the AC power flow equations as constraints that are sort of parts of bigger problems or different problems. These constraints are usually used in a wide variety of different problems. So if you happen to use this to try and solve a problem where your objective function is not such that it is sort of pushing towards minimizing losses, you might more frequently encounter that those relaxations are not going to be exact. So the objective function is actually a very important part. You could then try such things as what you see here, but you should also then be cautious to kind of say and draw direct analogies between these problems where this has been applied to problems where the original objective function is also trying to minimize the cost of active power or losses, because you could end up with quite different results depending on the objective function you started out with.
Yes, and I would generalize that statement to say anytime you modify the objective function, you should be extremely cautious about what a relaxation will do. They're very tricky. They're always trying to do something that's not feasible to the original problem, and so if you change the objective function, it's kind of like all previous results on the previous objective are out, and now you need to revisit, okay, how often is it feasible? How close is it to the true objective value? What are the gaps? So yeah, the objective function is a very particular thing.
Mm-hmm. Okay, so yeah, so to come to some closing remarks for this part, what we have shown here and tried to give you the intuition for is that the voltage products are really the core non-convexity in the AC optimal power flow problem. There are many established methods for relaxing those voltage products, and for those different methods for relaxing the voltage products give rise to a range of different relaxations of the AC optimal power flow problem. And these relaxations really vary in strength. That means like how close they are to represent the true AC feasible space, and computational time trade-offs. So there is typically such that a less strong relaxation will have a lower computational time, whereas the stronger relaxations will give you higher computational time. So the intuition for when do the relaxations work and not work is tightly related to how they represent the power flow losses and also Ohm's law. So having kind of good representation of those pieces of the problem are really sort of the challenges of the convex relaxations. And then we have seen, and it has been observed, that there are some convex relaxations that very frequently provide AC feasible solutions and are really kind of a jackpot kind of relaxations for those cases. But even for those relaxations, it is usually not guaranteed that you will be able to get solutions that are feasible for the original AC optimal power flow problem. And you need to be really careful to establish whether this is true or not for your particular kind of problem and your particular case that you are looking at.
Great. So in the next lectures, we're going to start to go over some tips for both using and developing convex relaxations of the AC optimal power flow problem. We're coming to like the culmination of all these videos, so that is the final capping one in this series.